All right, here we go with the first part of our lecture on chemical bonding. In this set of video notes, we're going to talk about Chapter 8 from our textbook, so obviously the basic concepts of chemical bonding. So 3 different types of bonds. 2 of them you're probably familiar with, 1 maybe you're not as familiar with. So the ionic bonds we've talked about, just that electrostatic attraction between ions, so when you have a positive and a negative next to each other, that they are getting attracted to each other. Covalent, you're also familiar with this one, the sharing of electrons. So you guys have probably drawn Lewis dot structures before and seen this kind of sharing of electrons. And these are going to be between different molecules, or between different non-metals. And then metallic bonds, where the metal atoms are bounded to lots of different things, and it's sort of like we sometimes call it a sea of electrons. The electrons are free to move around and create attractions that way, so you have this sort of lattice bound to lots of different things construction. We're also going to talk about Lewis symbols. So they're named after G.N. Lewis, who used this devised this symbol where basically we use dots to symbolize the valence electrons around an atom. And as we know, the valence electrons are really important for figuring out chemical properties and things like that. So like lithium has only 1 valence electron and has just this 1 dot to represent that, versus neon, we talk about having its complete octet, has all 8 electrons. So it's not really all that interested in bonding to anything else. You can see it doesn't have any space to do really anything. So that's where you're trying to get to, right? Tend to add or subtract electrons till you're surrounded by 8 valence electrons, and that's the octet rule. So to begin with, the ionic bonding. So a little bit about the energetics, because this is kind of strange. So we saw before that when we talk about ionization energy, taking away an electron, right, to make an ion, and it's a positive 496 kilojoules per mole to remove an electron from sodium. So you have to add energy to do that. And then we also saw that if you give an electron to something like chlorine, you get back 349 kilojoules per mole, so you get a negative number. Right? But when we add all those together, right, positive 496, negative 349, we get a positive number, which would indicate an endothermic reaction, right? You're putting energy into it. But in reality, that's not what we see. In reality, we actually get an exothermic reaction. We get a violent reaction going on here. And so that doesn't make any sense. So what's going on? There's got to be something else going on. There must be this third piece of the puzzle. And so what is going on is the electrostatic attraction between the newly formed sodium cation and chloride anion, right? So these guys are attracted to each other, and that's something that wasn't accounted for in the energetics of taking away the electron and then giving the electron to the chlorine. And so that is called the lattice energy. So it's the amount of energy to completely separate a mole of a solid ionic compound into its gaseous ions. And this is basically governed by Coulomb's law. And we're not going to really spend a whole lot of time with Coulomb's law, except that the idea is that based on this, you can see from the Q that represents the charge, so the greater the charge on the 2 different elements, the more attraction there's going to be. And then it's also over distance. So if they're farther apart, you're going to have a lower attraction. And so that basically translates into lattice energy is going to increase if you have a greater charge. And if they're larger, they're not going to be able to get as close to each other, and so you will see a larger ion will have a lower lattice energy. And so all this can be basically put together to form a nice complete picture. So these diagrams show the amount of energy being put in or given out of the system to get something done. So if we're starting with our products here, and starting with our reactants here, and these are our products, the red line is what that direct route would be. All right, and so this shows that we're getting a decrease in energy, so it's showing an exothermic process. And the green lines show everything that's happening to get there. So these are all the sub-steps. So we've got delta HF, so the heat of formation of sodium gas. So taking solid sodium and turning it into gas is going to require this amount of energy. And turning chlorine into gas is going to take this amount of energy. And then we're going to take away an electron. That's going to take a big input of energy. So now we have sodium plus and a free electron and just regular chlorine. And now we're going to give that electron to chlorine, and we're going to get some energy back. So now we're getting energy out of the system. all right? But we still have to get down here. And that difference in energy, that is the lattice energy. So that's how we can figure out what the lattice energy actually is, because we know that we're getting energy out of the system. So this is how we can figure that out. And they all add up to the same thing. In covalent bonds, atoms share electrons, right? And so there's lots of different things that control or that regulate these bonds. So the attraction between the electrons and the nuclei, right? So those, we've been talking about that before. They're connected to each other. So the nuclei and the electrons attract each other, so they're trying to go there. But there's also repulsions from the electrons. These guys are pushing each other away. And then there's also repulsions from the nuclei, because those guys are positive. So lots of different things going on. And we talk about this, really what it is we talk about sharing the electrons, but really it's just this concentration of electron density. Because remember, we talked about you don't really know exactly where all those electrons are. You kind of know the probability of where they are. So in something like this, you can see the probability map is they're most likely to be found, the darker blue, in between these two atoms. So that's the bond right there. And then the thing with covalent bonds, though, is that they're not always shared equally, right? So this would represent, this color map would represent electrons and where they are. If it's just F2, they are sharing it equally. But we've got hydrogen fluoride here, and the fluorine is very electronegative. You guys know this. And so you see a lot more electrons are over here. So fluorine is pulling much harder on the electrons that it shares with hydrogen than hydrogen does. So they're all concentrated over there. So the fluorine end of the molecule has a greater electron density, so it's more likely to be, it's a little bit more negative over here and a little bit more positive over here. Even though the whole thing as a whole, right, we don't have a positive or a negative sign indicated here. The whole molecule as a whole, we don't consider it to have a charge. So electronegativity, I know we talked about it, but this is becoming important again here, is just the ability of the atoms in a molecule to attract electrons to themselves, right? And these are some trends that we already talked about. As you go from left to right across a row, they're going to get more and more electronegative, right? Why is that? Because these elements are getting a greater nuclear charge, so they're pulling a little bit harder. And then the same thing from the bottom to the top, they're going to get bigger. Why does fluorine have a greater electronegativity than aluminum? Also because of the size. These electrons are going to be much, much farther away from the nucleus versus fluorine. The electrons are much, much closer to the nucleus. So they're experiencing a greater pull on that nucleus. So fluorine is going to be, as you can see, the most electronegative element on the periodic table. So back to polar covalent bonds. When two atoms are not sharing the electrons equally, so they're sharing them unequally, we say that a bond dipole results. And the dipole moment is when the two equal but opposite charges are separated by some distance. So we can calculate what that is. It's measured in this thing called dBys. That's how you pronounce that. And the greater the difference in electronegativity, the more polar the bond is. So as you can imagine, fluorine and hydrogen, very, very big difference in electronegativity, versus hydrogen and iodine, not as great a difference in electronegativity, so not as polar of a bond. So we're looking at 0.44 dBys versus 1.82 dBys, and big difference in electronegativity, 1.9 down to 0.4, and part of that has to do with the fact that they're farther apart from each other, right? These guys, the bond length is 1.61 versus less than 1 down here. So on to Lewis structures. What these are just representations of a molecule that show the bound electrons and the non-bound electrons. Just dots or lines. Sometimes you can draw them with dots here as well, and sometimes you just show the bonds as a line. And so when we're doing these, here's the process for it. So the first thing you have to do is figure out how many valence electrons you have in the whole kit and caboodle, in the whole molecule. Right? If it's an anion, then we're going to add an electron, right? Because it has a negative charge. If it's a cation, we'll subtract an electron. And remember, the valence electrons are only the s and the p, so we're not going to be looking at the d orbitals at all. So if we're keeping track of the electrons, phosphorus has 5 valence electrons. Chlorine has 7 valence electrons. There's 3 of them. So we have 26 electrons that we're dealing with. There's no charge on this molecule, so we don't have to add or subtract any electrons. The central atom, the one that we're going to put in the center, is always going to be the least electronegative element, as long as it's not hydrogen. So that's one we would put in the center, and we connect everything else around it with single bonds. So if we do that, we've got our phosphorus here, we put in our chlorines. These guys all represent 2 electrons, 2, 4, 6. So 26 minus 6. Now we have 20 electrons left to assign to our Lewis dot structure. So what we're going to do is place the rest of them to fill the octets of the outer atoms. So boom, 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 boom. So this guy is now full. It's got 7, because remember this represents 2, or I'm sorry, it has 8, because this represents 2. Same thing here, same thing here. So we had 20, then we assigned another 18 electrons. Now we have 2 electrons left that are still unassigned. So we'll use those and fill the octet of the central atom. So now phosphorus has 1, 2, 3, 4, 5, 6, 7, 8. We have no electrons left. We're happy, usually. If you run out of electrons before the central atom has that octet, then you form some double bonds. So here, we don't have any more electrons to put in this molecule, but carbon's not happy. Carbon only has 4 electrons. So what we can do is we can take some of these electrons from nitrogen and move them down here to form a triple bond. And now carbon is happy because it has 2, 4, 6, 8. And nitrogen is happy because it has 2, 4, 6, 8. And hydrogen is still happy because it only wants 2, right? So everybody's happy, and you've got a triple bond in here. I said earlier that you're almost done. Well, sometimes there's different ways of drawing things, and you have to figure out which is the best way energetically to do that. And that's done by assigning formal charges. So for each atom, you're going to count the electrons in lone pairs and then half of the electrons that it shares with the other atoms. And you subtract that from the total number of valence electrons for that atom, and you get formal charge. Okay, so if we look at 2 different ways that we could draw CO2. Okay, we could have carbon in the middle, double bound to 2 different oxygens. So oxygen, its formal charge, it has 6 valence electrons, and the number of electrons that are assigned to it, 2, 4, and then half of this, so that's 4 electrons, half of that is another 2, so it has 6 electrons assigned to it, its formal charge is 0. Same thing for this guy is 0. Carbon has 4 valence electrons, and you have 2, 4, 6, 8 bound electrons, but we're doing half of that, so that's 4. So everybody has a formal charge of 0. You could also draw it, like I said, this way, right? This still fills all the, or satisfies all the rules that we just stated. Oxygen has 6 valence electrons. If we look at it, how many electrons are assigned to it? 2, 4, 6, and 1 here is 7. So now it's got a charge of -1. This guy is still a 0, but this oxygen has fewer assigned to it, so now it's a +1. Okay, so which one is better? The one with the fewest charges is going to be what you want. So if it's a 0s all across the board, that's good. Sometimes you can't always do that, so you're going to put the negative charge on the most electronegative element. So if we're looking at these guys here, who's going to be the most electronegative? Well, that's going to be oxygen. So if we can't get 0s all the way across the board, which we can't, we're going to want to put the charge, the negative, on the oxygen, because that's going to be the one that's most electronegative. It's going to be the most likely to grab onto electrons. It's going to be the one that's most likely to be a negative formal charge. So in this case, this is the best Lewis dot structure to draw for this molecule. Next, we're going to talk a little about resonance. This is a structure that you can draw for ozone, O3, right? So you have to have a double bond here, and you can do a single bond. All right, so that's great. But when you look at what we actually see, it doesn't really jive with that diagram, right? This shows us that we have a double bond and a single bond, so those would actually be unequal bond lengths. This would be, one would be a shorter bond. But when we look at the like the overall, everything in ozone, wait a minute, this is the same, right? We don't have that difference. And both of the outer oxygens have a charge of -1/2, right? That also doesn't make sense. So what's going on? Well, in reality, one Lewis structure cannot accurately depict the molecule like ozone, right? You could draw it like this, or you could draw it like that. They would have the exact same formal charges, right? This oxygen would be different than this oxygen, but overall, everything's the same. So this we can use multiple resonance structures to describe this particular molecule. right? And just like blue and yellow make green, we can take this resonance structure and this resonance structure, and if we blend them together, overall, when we're looking at a whole bunch of ozone, right, we're going to get a blending of those, and they basically balance each other out. You get a synthesis of these two resonance structures, and if right, everything cancels each other out, and you end up with equal bond lengths and equal charges and everything like that. So in truth, the electrons that form that other CO bond just basically, they don't always sit there, right? They can move around. We talked about that. Because all we know is the probability of where they would be. It's just the distribution, the density map. In this case, we say they're not localized, they are delocalized. So they are able to move, right? And so you get different electron resonance structures. They could move here, they could be here, they could be here. It's back and forth. You would also see this, or the way we depict this in some molecules form rings, right? These like hydrocarbon rings, C6H6. And you see you've got like double bond, single bond, double bond, single bond. But this could just as easily be a single bond and sort of like the same exact thing. It's just shifted around once. So you could draw out resonance structures like this, where this is your double bond, single bond, double bond, or sometimes you'll just draw this circle in here. So if you see that circle, that's showing that those electrons are delocalized, and they're in that ring, and they're just somewhere in there. So that's one way of depicting that you've got some resonance going on in there, different resonance structures. Also, there's some other complications when you're doing these Lewis-Dach structures. There's 3 different ions that don't always follow that octet rule. So one, there's some ions or molecules that just have an odd number of electrons, and it's just not going to be possible, no matter how you do it, to fill your octet. Some things are happy with less than an octet, and some things are happy with more than an octet. You can actually expand on that octet. So though relatively rare, sometimes things do combine together. Like this guy here, there's just not enough electrons to get everything you need, right? You can fill oxygen, but there's not enough to fill nitrogen. You can fill nitrogen, there's not enough to fill oxygen. And that just sometimes it happens, and it's rare, and they're not unstable, or they're very unstable and reactive because they want to do anything they can do to fill that octet. So we don't see them a lot because that's not a very favorable form, but it can happen. Sometimes you can get things that are fewer than 8 electrons. That's just better. So for example, if we're looking at BF3, if we fill the octet of boron, right? So in this example here, boron has 2, 4, 6, 8. It's got its octet filled. But now when we assign our formal charges, we're putting a negative on boron, and fluorine, right? Fluorine, the most electronegative element in the periodic table, has got a positive charge. That just doesn't make sense. So therefore, the structures that put a double bond between boron and fluorine are actually much less important, right? You wouldn't see that as much as this guy here, because this guy is going to give our negative charges to fluorine, which is where you would expect to see them, right? So basically, the rule of thumb is if you're going to fill the octet and it just doesn't make any sense with the formal charges, in this case we're putting the negative charge on the central atom and a positive charge on the more electronegative outer atoms. Remember, the electronegative ones are what's going to be on the outside. That just doesn't make sense. So if that's the case, draw it a different way that leaves the electrons or the octet of the central atom unfilled. And again, that comes back to formal charges. You would see that you would have a more sensible arrangement of formal charges. And then some things can get more than 8 electrons. So you say, all right, we've got this molecule PCl5, right? The only way that's possibly going to work is if phosphorus has 10 electrons around it. There's no 2 ways about it. So how does that work? Well, generally speaking, if it's in the 3rd row or below, you're allowed to expand the octet. So presumably you've got some d orbitals that can participate in the bonding. So phosphorus would look something more like this. So it's got 10 electrons here, and everybody's happy with their octet filled plus phosphorus with some extras. So that's the key thing, though. It's in the 3rd row or down. So you're not going to have, oxygen's not going to have an expanded octet, but sulfur might have an expanded octet. So again, here's another example. even though you could draw a Lewis structure for this phosphate in PO4, phosphate ion, with 8 electrons around phosphorus, now you're ending up with this +1 here and all negative ones, which doesn't seem so bad, but if you were to just throw in a double bond, now you're getting a 0, 2 zeros here and 3 negative ones, and so that's better, right? This guy's down to, remember, the fewer charges you have, the better off you can be. So in this case, because phosphorus is able to, it's third row or down, this is the better option for the phosphate ion. So it eliminates the charge on phosphorus and the charge on one of the oxygens. So if the central atom is in the third row or below, and you can expand its octet to get rid of some of the formal charges, you can go ahead and do that. A little bit about bond strength. So basically, simply put, the strength of the bond is how much energy it takes to break that bond, right? And that's called bond enthalpy. So the bond enthalpy of a Cl-Cl bond, we say this D parentheses Cl-Cl is measured to be 242 kilojoules per mole. So it's a positive number. We have to input energy to get that bond to break. We as in chemists have done lots and lots of experiments to calculate bond enthalpies, and so you can look these up, right? They're table 8.4 in your book. So you can look up just about any type of bond and see how much energy it's going to take to break it. How much does a CF bond take? Oh, it's going to take 485 kilojoules per mole. Again, they're positive because it takes energy to break a bond. And if we look at this, a single bond is going to require less energy than a double bond is going to require less energy than a triple bond, right? So like here's CO triple or double bonded 799, CO triple bonded 1072. All right, and N together, right? 163 in a single bond, 418 in a double bond, 941 in a triple bond. So triple bonds are they're stronger, right? Just like you'd expect. You've got more electrons in there holding things together, right? One piece of duct tape versus 3 pieces of duct tape. Which one's going to be harder to break? And again, these are average enthalpies, right? Because sometimes you're going to have, like, there's going to be slight differences between the CH bond and something like CH4 versus CHCl3, right? They're not going to be exactly the same because of polarity considerations and dipole moments and things like that. But so this is on average. This is what you can work with. So you can also talk about enthalpies of an entire reaction. So you can estimate your delta H, your heat, for entire reaction by comparing the bond enthalpies broken to the bond enthalpies that are formed and calculate the delta H of your reaction. So the delta H of the whole reaction would be the sum of the bond enthalpies of broken bonds minus the bond enthalpies of the bonds formed, right? So if we're going to be making this, right, we've got to put these guys together. So we're going to do that, we got to break some carbon-hydrogen bonds. We're going to break the chlorine-chlorine bonds. So we've got to bust off one of these guys. We've got to separate these guys apart. So now we've got a CH3 plus an H, 2 Cls. We're going to stick those together. We're going to make a CCl bond and an HCl bond. And so we're going to get some energy that way. And it all adds up in the end. So this is basically what I just said. So to figure what the actual numbers, right, so delta H, right, so you have the 413 kilojoules of the C to H bond plus the 242 of the Cl to Cl bond, and we're going to take away the energy from the C to make the CCl bond and the HCl bonds. So overall, 655 minus 759, and so overall this is going to be an exothermic reaction, negative 104 kilojoules, which is what we expect, right? This guy is lower, our products are lower down here, enthalpy is down, so it's going to be a negative number. You can also measure the average bond lengths for the different bond types. So similarly, like these guys are averages, right? And as the number of bonds between the two atoms increases, the bond length decreases. So a triple bond, they're going to be very close together versus a single bond, they're going to be much farther apart, right? Carbon to carbon, single bond, you got 1.54. They're a little bit closer, 1.34 when you're a double bond, and when you're a triple bond, now you're down to 1.2. So they're held a little bit closer, which also makes sense because they're stronger, right? So they're held more closely together. And that is that.